we're going to talk about the formation of an organocopper reagent from an organolithium reagent. So if you've already made the the organolithium reagent, we'll use the same one we had previously, which can also be written as either of these is actually correct, but again, I like this bottom one more because it describes that the character is more. This is really an ionic complex. You really do have more positive and negative character by a long shot than you do covalent character where you're actually sharing electrons. What's going to happen is this chemical species is put in solution with copper iodide, and this is copper 1 iodide. And again, this is how your book is drawing it. But what you have again is a Cu plus 1 and an iodide with a negative charge. Now, copper is actually one of these metals that is a transition metal, so it can have several different stable oxidation states. The most common are a plus 1 and a plus 2. And we're going to see how this one actually goes to a plus 2 as it gains an electron. Or sorry, it's going to lose an electron. I'm not telling you good things, but we're going to look at this process. So I'm going to look at this organolithium reagent again. This is a very reactive chemical species because they really are not well associated with each other. What you again really do have is the carbanion and lithium cation. This is really what you have. And copper iodide, they actually hang out together fairly well as a complex. The difference in electron negativities is not large, and so they hang out fairly well together. But this carbanion that we have over here is extremely basic, as we've mentioned previously. And because it's so basic, it really needs to give the electrons to someone that will share them with it. Iodide's already negative. It doesn't want any more. Lithium is no help, but copper is a different metal. And copper is more electronegative than lithium is. If you remember, lithium has an electronegativity of 1.0. Copper is 1.9. And so it's quite a bit more electronegative. It's still electropositive. It's a metal. But it's going to be able to share these pair of electrons with the carbon to a much greater degree. Again, carbon's electronegativity is 2.5. So the difference in electronegativity between carbon and copper is only 0.6. Now that's in the polar covalent region. It's not quite covalent, but it's in the polar covalent region. They actually can share the electrons. It's not going to make a completely ionic complex. So this pair of electrons here comes over and decides, do they want to pair up with the copper? And iodine gets pushed out. And this will result in copper being bound to the carbon chain. And then you have your lithium paired up with your iodide. And this is more favorable because now we aren't so much like this. I mean, there's still some ionic character associated with these two, but they actually do spend more of their time bound to each other. They like to share a little more. And this is why that anion jumped to copper over lithium. It shares the electrons better with this carbon. And carbon wants to share electrons with someone. It doesn't want to be a strong base. This is why this is favorable. Well, copper, like I mentioned before, is one of these metals that can undergo different transition states. And so it's going to accept some more electrons from another organolithium complex. There's our organolithium complex, which again really is the carbanion and the lithium. And then we have our complex from the last piece. So another one of these anions says, hey, copper, I'd like to hang out more with you than I would with lithium. Is that okay? And so we're going to give the electrons to the copper. Copper is going to accept them. And that's okay. Copper can do this. So what you end up with oh, I dropped a carbon, sorry, is this guy. And overall, there's a net gain of an electron, or net loss of an electron for copper. But copper is the whole piece here. This dialkyl cuprate has a negative charge, and that will be associated with this lithium. What you really have for this complex are two carbanion pieces. So there's two negative charges, and then your copper, which was a +1. And since it's accepted electrons, it's had to gain another electron. But it can do this. As you can see, the charges will balance here. You've got the two positives, this guy and this guy are your positives, and you got the two negatives. But this is the complex we're going to form, because copper can form these two bonds, and overall that piece has a negative charge. The copper will form better bonds with the carbon than the lithium did. This is a more stable complex. And as a result of that, it's a lot less reactive, and you can do very different chemistry with it. What we typically do with an organocopper reagent is we use it to make carbon-carbon bonds with other alkyl halides. So here's our species. And you would usually see this on top of the arrow in diethyl ether, because again we still need to avoid acidic protons. But this is what you're going to see on top of the arrow. And over on the reagent side, you're going to see some alkyl halide. Now I'm going to keep this real simple because I don't want to spend a lot of time drawing one. But you have an alkyl halide. These tend to work best with methyl groups, though they do work fairly well with primary alkyl halides as well. Secondary and tertiary, not so much. I'm not saying it's impossible, but they don't work real well. And they work best as you have really good leaving groups, like para-toluene sulfonic acids, any of the halogens, but iodide best, then bromide, then chloride, and fluoride being the worst. They're not entirely certain how this mechanism works, so I'm not going to pretend to know. But typically what you have is two equivalents of the alkyl halide, and it reacts with these two alkyl chains attached to the copper, so that in the end you produce a carbon-carbon bond, and here you produce two of those, and then you would have your copper associated with iodine and your lithium associated with the iodine. But you make carbon-carbon bonds, so you've made one here and you've made one here with each of those two alkyl halides, and they each react with the two carbon chains attached to the copper. So there were three that are circled there in red and one in green. Overall, you get a butane.